So tonight we have mainly two topics. One is a continuation of the topic of graphs, and then I'm also going to talk about hashing. So the sequence in which we will go is that I'm going to first address one question that was asked last week on the quicksort. How does it work out when there are repeated keys? I just want to make sure that you are able to appreciate how exactly it is working efficiently in the presence of the same keys, and particularly when the same keys are chosen as pivot. There are some subtleties which you may not have observed, but I wanted to give you some time before you start working on your homework so that you have some experience of understanding the workings of the quicksort. So I'm hoping that you all have got your hands dirty, and now you would be able to appreciate this point. The question that we wanted to explore is that, so when there are items with same key as the pivot, what is happening in that case? So let's take an example. So suppose I have all the entries as the same entry. Okay. Now recall in our approach that that we shared, we brought in the pivot here. So this is the point where the pivot is. So it got swapped, right? And brought into the last position. But in this case, everything is 6. So so you can imagine that it doesn't matter which 6 got swapped. And then we also, the way the setup for the in-place quicksort algorithm is that you have the, so initially you have the I position here and the J position here, and you're trying to sort in between with the array A. And we got the index M pointed to one element just before it, which is essentially set up to M equal to I minus 1. And then we had the N here equal to J. And we are moving the N pointer, or decrementing the N pointer backward, and the M pointer is going forward. So I hope you recall this setup for the in-place quicksort algorithm. So what's going to happen is that we want to advance M to the key that is greater than equal to pivot. And this is the question that we are trying to explore, that why is it not greater than, and instead it is greater than equal to. And likewise, it is decrement N to key that is less than equal to pivot. And once it has come to the point where it is greater than equal to pivot and less than equal to pivot, wherever the M and N is, we perform the swap operation, right? So we swap items at M and N after going through this process. And we talked about the rationale is that wherever M and N stops, anything to the left of that is going to be the is going to have the keys that is going to be less than A of M, and wherever the N is stopping, the keys on the right should be greater than the key that is there at position A of n, right? So you recall that. Now one may ask, like, if all the entries are equal, why go through this swapping operation? Isn't that this swapping completely useless? Any thoughts? Okay, so let's see this in action, then you would be able to appreciate. Suppose I did not decide to go ahead and swap even the entries which are equal, right? Then what's going to happen is that I'm going to keep on advancing m until I reach the end point, or I find something which is greater than the pivot, right? Because that's the first step. So if I draw the same entry here, so what's going to happen here is that, so you can see, so the m got decremented, so it becomes, sorry, m got incremented, so m will come here, and it sees that, okay, my pivot is 6, okay, so 6 is not greater than 6, so it's not going to stop, keep going forward, keep going forward, keep going forward, keep going forward, keep going forward until it reaches here. So what we are going to see here is that after going through this process, if this is not greater than equal to, but it is greater than, then it is going to end up reaching here, where m and n would be both pointing at this location. You got this point? Any questions so far? So what do you see as a result of this? So you can see that that has the same skewed effect what we saw when we were choosing a very poorly designed pivot selection algorithm, where we would end up having n square complexity. So here also, likewise, the effect of not actually swapping has resulted in this. So suppose now we follow exactly what we have stated here. Then what's going to happen is, so you have your pivot here, and if we are stopping at the key equal to pivot, so m will stop here for the first time, right? And n will also get an opportunity to move forward, move backward and stop here. And then there will be swapping. Completely useless, looks like, but there will be complete swapping here. Great. Then m will again move forward. Next, m will come here, n will come here. There will be swapping. And then m and n will both come here. Okay. So instead of m and n reaching this end location, and as a result of which getting a skewed sort of distribution of the whole algorithm, by enforcing the swapping to happen with greater than equal to and less than equal to, you can see we are able to have a very even distribution of the whole thing. So 6 is here, 6 is here. And as a result of which, the algorithmic complexity would remain as n log of n in the presence of multiple entries. So it's a very, very subtle point, but very important for us to appreciate that every single detail matters in order to create an efficient algorithm. Any question? Is this point clear?
Wait, so the pivot always stays at the last item value, or pointing to the last item, is that correct?
Correct, but we are making a swap, right? Then pivot comes to the middle. The next step is to bring back the pivot to the middle, right? That's how the whole split happened. So this is the left side of the pivot, and this is the right side of the pivot. So everything on the left hand side remains less than or equal to the pivot. Everything on the right hand side remains greater than or equal to the pivot. But by enforcing this swap, unnecessary so-called swap, we had been able to give a split in the middle. That's what we were able to do in this particular case. Is this point clear? Okay, I'm assuming it's clear. So let's stop the